Fortress is a precast modular concrete building that protects against an array of hazards. Those hazards include blast, fire, fragment, toxic, and extreme weather events. And these buildings are often used at facilities that handle hazardous materials. We saw that there was a need for a building that offered multi-hazard protection. A lot of other buildings that are out there right now really just focus on one aspect, and that's usually the blast-resistant aspect of protecting people. So it misses fragment hazards, it misses toxic hazards, it misses fire hazards. So we knew that there was really not a building out there that was able to offer people the protection that they deserved. We ended up settling with a precast building. Precast construction is an expedited form of reinforced concrete construction where it's done off-site at a controlled facility. And the reason why we did that was just so that we would have that quality control off-site, but also precast is just superior to most other building materials. After we went through doing all the design and thinking about what could work from a practical standpoint, we wanted to really prove out our analytical models and make sure that we were providing people the protection that we were telling them would be able to provide them with. Fortress performed better than what we had expected and better than counterparts would. Blast tests, we have representative samples of those, and we tested those numerous times, up to 7 times in the shock tube, and the wall system continued to perform well. Most buildings are designed to incur a certain level of damage, and that's acceptable, but when we're putting a building, which is an important building, right near a process, and it's a building which has critical controls in it, we want that building to be operational following an event. So that's why we repeated testing. But we want people to understand that even though you're seeing some damage, the building's still okay. So we hit it again with the design load again, and then we hit it again, and then we hit it again. And you continue to see increasing levels of deflection, as one would expect, but the wall has such a large amount of resiliency and ductility that it all held together, and it's still standing out in our specimen yard 3 or 4 years later. All right, so we're gonna look at the specimen here. This was tested in the shock tube. This was actually tested 7 times. So this would be the inside space of a building, the protected space. This is our door that is in our vestibule, and you can see the door is still operational, even after being tested as many times as it was. So this wall was tested up to blast pressures of 20 psi, impulses of almost 1400 psi milliseconds, which is a huge load in terms of both pressure and duration. The way that we constructed this is a precast wall, and all the holes around the perimeter, those were used for bolting into the shock tube. And the reason we did that was to mimic the boundary conditions that you'd get in an actual vestibule. So this vestibule is cast as one entire piece, which means you have continuity and fixity around all the edges. And so we wanted to mimic that by bolting it to the shock tube with these steel plates here. This next wall that we're going to look at here, this is a specimen that's tested in the shock tube again 5 times. You'll see a number of cracks on it, and that's because we hit this with the design basis load 5 times. The impressive thing about it is that the wall is still really resilient. It's been standing out here for a couple of years. It would hold up against any kind of environmental loads. This is the joint that is basically the mating surface between 2 of the precast modules. So the precast modules are seated adjacent to one another. They're bolted in place, so there's no welding at all. It's all bolted. And so you can see the bolts there. And then within this joint, we've got a series of fire ropes and intumescent caulks in there, and then also a weather seal as well. So that joint itself is also very resilient. We don't have it out here, but we also tested this wall with a jet fire with a direct impingement to test that joint, and the joint held together very well there again. Okay, this wall here, this is similar to the wall that we looked at with the blast door that was tested in the shock tube, but the unique thing about this is that this was actually tested under a direct flame impingement for up to an hour. You can see a still capture here of the actual test itself. And what we were doing, we had a structure behind it, and we were actually measuring the temperature inside that structure. And these tests were done in the heat of summer in Texas in July. And even inside that space that was unair conditioned, it didn't get above 110 degrees. So the door itself, this design has actually changed since we ran these tests. The door is now a stainless steel door, so you wouldn't have corrosion like this. We also have stainless steel frame around it as well. So we made some improvements that came out of these tests. The real impressive thing is if we just look inside the wall itself, is that if you were standing here, you really would have no idea that this was exposed to a fire. So if you think about like a house fire, for example, you see charred wood from both the inside and out. This, you still have extreme protection on the inside of the building. These two specimens here, these were used for fragment testing. So we mounted these in a fixture and we shot some steel projectiles at them at very high velocities. And you can see very low impressions of scabbing on the front face of, this would be the outside face of the fortress building where those projectiles hit. So this has been hit in a couple of instances. We fired steel projectiles, it's actually been hit 3 times. And those projectiles were 13-pound plugs traveling at around 200 feet per second. In contrast, we did this with steel. Unfortunately, we don't have those over here, but it just tore through those panels. So when we ran our shock tube test, what we wanted to do is really test this joint and exercise that. So the specimens that you see are essentially a slice halfway between each of these walls. So slice there, a slice there, and we're loading this entire surface as though there's a pressure from the outside of the building. And so again, we're exercising this joint, seeing if it holds together, and then if it would, survive the blast test, and you'd still be able to use the building as intended after the design basis event. This is our fortress vestibule. This is the entry point into the building. When we looked at the specimens before, essentially this wall here was what we were testing in the shock tube and also the jet fire test. This is the fortress door. We're going to open it up and have a look inside. It's a 4-inch thick stainless steel door with thermal insulation inside of it. The same door that was tested for fire hazards and blast hazards.
Welcome to our fortress nameplate number 1. We're going to start this tour of our fortress here in the vestibule. The vestibule is an option on the fortress buildings, but it does add an additional layer of thermal and toxic gas protection. It also is a great place to use as kind of a weather mud room. You can come in, drop your stuff. You can have hard hat hooks, boot mats. But also you can see that we've got our toxic detection here. So while we're detecting outside and as well the roof air intake, we're also detecting in this space so that we can show the gradient if there is a toxic event as you walk into the building. So walking into the main structure, this is what we call our main utility corridor. You can see the main HVAC system running down through the roof line. We've got our fortress set up so that we have a kitchen over here, so a break room, and then we have our training room. So this whole side of the fortress is actually open plan. Another open plan option that you can do is actually your control center. So you can think about your control boards and your operators sitting at your control boards in an open area. We have this side set up as offices and separate rooms, starting with a restroom. And so here you can see that there's sink, shower, restroom. A lot of clients are actually expanding this area to have a change room, locker rooms, multiple showers so that they can really have an operator shelter that's fully functional. Continuing down the utility corridor, the next room we're going to come to here is what we call our mechanical room. Washer, dryer, but the big thing here is the air handling equipment. Again, air intake is just above this on the roof. Toxic gas detection there. If it detects toxics, 2 out of 2 voting, it actually shuts down this system so that it stops bringing in air from outside, which becomes very important as we move on to the next area, which is actually an office, but it's also an interior shelter in place room for toxic materials. And if there was an event, this is where you would come for that additional layer of protection. This control box over here is where you're going to see your readings from all the detectors that we've discussed so far, but it's really going to give you the information of how safe you are in this building and whether you need to stay or eventually evacuate if you can't bring the event under control. What you see here is an air system. You can connect bottled air here and it creates a slight release of air into the space to keep it habitable for a longer period of time. And we're going to leave Fortress through another vestibule. It's another 10 by 10 by 10 for that added toxic and thermal protection. You can see we've offset our door on this side for flow purposes. You can do that. It can be on any of the sides that are needed. And thank you for touring our Fortress today.
I would say that Fortress is going to offer you, again, not just blast protection, but protection against toxics, fires, fragments, a lot of hazards that people don't consider and they should consider if they look at API 752 and API 753. The primary focus, and it's in the name, blast-resistant modules that people buy blast, and that's what they're focused on. They're not focused on the other hazards, which we probably see incidents and accidents occurring more often from those hazards than explosions themselves. You're investing a lot of money into a building from the startup, And you want to be buying something the same as you'd buy any kind of consumer product that you want reliability. Well, if an event occurs and you have an explosion, you can still go back and use that building. And that's some reassurance for clients.